In this screencast, we'll talk about Euclid's second theorem and its implications for computer science. So we'll begin with a simple number theory factoid, which we will state without a proof, as it's pretty easy to prove, and we will use in proving Euclid's second theorem. So let A, N, and B be natural numbers. Then if A is equal to n plus 1 and B is greater than 1 and B divides A, then it is not the case that B divides n, right? Or B does not divide n. You can prove it by contradiction, by assuming that B divides n and then reaching contradiction. Right, so this would be a useful exercise. So here's an example. Let's say that A is equal to 5 plus 1 and B is equal to 3. Then 3 divides 5 plus 1, right? A divides B, but 3 does not divide 5. So let's define Euclid numbers. And give a formal definition of a Euclid number. So we have primes 2, 3, 5, 7, 11, 13, 17, and so forth. Then let P sub I be the ith prime. Then the ith Euclid number is defined as the product of all prime numbers from 2 and up to P sub I, the ith prime, plus 1. So E sub I is the ith Euclid number. I give you a couple of examples. So P sub 0, by this definition, is 0. So 0 is not a prime, but we need to bottom out somewhere, so that we start the start counting actual primes from P1. So the first prime is 2, the second prime is 3, the third prime is 5, and etc. So what is Euclid's second theorem? Euclid's second theorem essentially states theorem that there are infinitely many primes. And there's another formulation of this theorem that you may occasionally see in number theory books or some algorithms books that use primality, especially if they discuss encryption algorithms. Given a finite sequence of primes, 2, 3, 5, up to um, p sub I, right? Some ith prime. Uh, this ith Euclid number e sub I, which is equal to the product of all these primes from 2 and up to and including p sub I, plus 1, p sub I plus 1, is either a prime or, and that's a very important or, it is divisible by a prime number greater than, okay, either a new prime, right? That's very important. New prime, right? Or is divisible by um, a prime divisor. So it has a prime divisor greater than p sub I. Let's see if we can prove this quickly using our number theory factoid. So we're going to use a contradiction, the contradiction methods, and assume toward a contradiction that there are finitely many primes. So in other words, the number of primes is finitely many primes. The number of prime numbers is finite. Okay. So then the a direct consequence of that assumption is that there will be some enumeration, finite enumeration of these primes, beginning from 2 and ending with some largest prime, p sub I. So consider e sub I. This is the ith Euclid number, which is equal to the product of these primes, 2, 3, 5, p sub I, plus 1. Right? Then, there are two things, two possibilities for this number. E sub I can either be itself a prime, or if it's not a prime, then the only other possibility, since it's a natural number, is that it is a composite number. It's a product of two other numbers, neither of which is equal to 1. So if E sub I is a prime, then we're done, because we actually have found NU prime, which is not in the list of, in our finite list of primes. So we have found a NU prime, a prime greater than p sub I, which is the largest prime. Okay. We found our contradiction. So if A sub I is a composite number, then by a theorem that we proved in the previous screencast using the well ordering principle, E sub I must have a prime divisor. However, by our factoid discussed the beginning of this screencast, that prime divisor cannot be 2, 3, 5, or any of the prime numbers from 2 or and up to p sub I, right? Because the prime divisor divides E sub I. So hence it must be a prime greater than P sub I. And again, we have found another prime which is greater than P sub I and which is not on our list. So hence the number of primes is infinite. Okay, we'll continue.